All right, we are looking at right-angled trigonometry. So to start, we need to look at properties of right-angled triangles. So that means one of the angles is a 90-degree angle. So you've been dealing with these triangles for a few years. You've learned about the Pythagorean theorem and the relationship between the sides in a right triangle. So in the first part here, it says, find the missing side for each of the triangles below, round to the nearest tenth. So taking a look at this, we need to enter a bit of information because we did not put a 90-degree symbol in there. So just be aware of that. That is a 90-degree triangle. And so remember the Pythagorean theorem is c squared equals a squared plus b squared. Okay, this is the hypotenuse. These are what we call the legs of the right-angled triangle. Okay, they're the sides that surround the right angle. Okay, so looking at this, this is your hypotenuse. I get into the practice of labeling the sides. So hypotenuse, and these are your legs. Okay, so that means 21 squared equals x squared plus 15 squared. Really, we want to solve for x squared. So we're going to, you may have done this right away, shown it as a subtraction. Then you don't really need to see every step, so you can get out your calculator and go 21 squared minus 15 squared, and that's 216. And remember, that's x squared. So we need to square root. So x is the positive root because a side cannot be negative. So the root of 216. And remember, in a graphing calculator, you can do second negative to get the previous answer. And it says round to the nearest tenth, so 14.7. Then take a look. No units are given on this triangle. You're looking for a leg. Make sure that it's smaller than the hypotenuse. The scale on this triangle isn't perfect, but not too bad. It looks a little bit shorter than 15, and it is a little bit shorter. Probably should be a little bit closer, but and for sure it's less than the hypotenuse. So do a mental check like that. Next one, right angle triangle. Now we're looking for the hypotenuse. So x squared equals 5 squared plus 3 squared. So that's 25 plus 9 is 34. So x equals the root of 34. Okay. So root of 34. Oops, I did the wrong thing there. Second, x squared is root of 34, and that's 5.8. And the units are given here. So 5.8, take a look at it, make sure that that length is a hypotenuse, right? Make sure it's longer than each of the legs of the triangle, and it is. Another thing that we have to talk about are similar triangles. So you've learned about these. Here's two triangles. These are examples of two similar triangles. So when you take a look at these, you can see that a little bit hard to see. Hopefully your note sheet worked out okay. This is 5 here. I'm just going to make them bigger. 10. This is 4. This is 8. This is 3. This is 6. Okay, notice how the angles are labeled with the same Greek letter. So that's alpha, okay, and this is beta. Okay, so within the context of two triangles together, if they're labeled with the same symbol, that means they have the same measurement. So that means the corresponding, and certainly they're both 90 degrees, so the corresponding angles are equal. Okay. Then it doesn't have to be a 90-degree triangles, the two of them, to be similar, but these ones are 90 degrees. And then as well, take a look at the ratio of sides. So for example, ratio of AC in the large over AC in the small. So that's 6/3, which is 2. We take a look at the ratio of CB in the large over CB in the small. That's 8/4, which is equal to 2. And then if we look at AB in the large over AB in the small, that is 10/5, which is 2. As long as these are all the same, then that means the sides are proportional. I'll call them corresponding sides are proportional. Okay, and those are the two properties of similar triangles. Okay, for a 90-degree triangle as well, within the actual triangle, corresponding sides within each triangle will also be proportional. So if we take a look here, if we look at, what is that, CB in the large over AC in the large, we get 8/6, which reduces to 4/3. If we look at the small triangle, we get 4/3. Okay, so they're also proportional as well. So that's looking at similar triangles, and that's really the basis of trigonometry and the trig ratios that we're going to use. Notice the word trig ratios, because we're going to look at ratios of sides. So within a triangle here, that's why this is important, right? Because in the big triangle, that ratio is the same as in the little triangle. And the angles are all the same. So that's really going to be important in terms of trig ratios. So we want to say this in words too. Ratios between corresponding sides within each triangle are equal. Okay. All right. So let's look at some summaries here. So opposite and adjacent side to an acute angle. So the legs of a right triangle are given special names relative to one of the acute angles. So when we were talking about Pythagorean theorem, we didn't care which leg was which, right? We just had two legs. Now we're going to label them specifically. So if your point of reference changes to the other acute angle of the same triangle, opposite and adjacent sides will change as well. So you always have to know which angle you are referring to. So here you can see, we'll circle it, angle A. So this side here is opposite because that side does not touch any part of angle A. Okay, adjacent to angle A because that side here, adjacent means touches. It's part of angle A. Okay, and then this would be the hypotenuse. Hypotenuse is always opposite the 90-degree angle, but we don't call it opposite. Opposite's used for opposite of an acute angle. And remember, acute means less than 90 degrees, greater than 0. We'll just keep it like that. Okay, so here's a diagram. Label the sides that are opposite and adjacent to angle B. Circle it. Okay, so this longest side here is the hypotenuse. So it is adjacent to B, but it's more specifically the hypotenuse. So this side is adjacent. It's touching angle B along with the hypotenuse, okay? And then the side that doesn't touch angle B is the opposite. Okay? We know we'll only talk about the side opposite and adjacent to an acute angle, never the right angle. Yeah, that's what I just said. Hypotenuse is opposite the right angle, but we don't call it opposite. It has a more specific name, which is the hypotenuse. Next screen here. So, trig ratios. The three sides of a right triangle can be compared to each other using ratios called trigonometric ratios. Each of the trig ratios has a special name. The three primary trigonometric ratios are, they're in the box here. So sine, that's the full word, S-I-N-E, of angle A, okay? Abbreviation is S-I-N, but it's not pronounced sin. Math is not a sin. So we still say sine, but we abbreviate it to 3 letters, and that's what you'll see in your calculator. Next one is cosine. That's the full word for it. We often abbreviate it to cos, okay, which is here. Cos looks like cos, but again, we say cos because the word is really cosine. So we want to abbreviate the word. And then tangent is abbreviated to tan, okay? And that's easy. Tan, it looks like tan. Tangent has other meanings in mathematics. So the context of the question is important. At this level, tangent is always going to be a ratio of sides in a right angle triangle. Okay? What are the ratios? So for sine, it's the length of the side opposite to A over hypotenuse. So abbreviation, opposite over hypotenuse. Here is adjacent over hypotenuse. And this is opposite over adjacent. Okay? So sometimes you will see O over H, A over H, O over A. And sometimes you may have heard of an abbreviation. Remember, this is for sine, this is for cos, this is for tan. So you can even look on YouTube, find some nice little music videos. SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tan is opposite over adjacent. If you need a little trick to remember. Okay, so does the sine, cos, or tan of an angle depend on the size of the triangle? No, because it's a ratio of sides. So no, these are ratios of sides within a triangle. Okay, and therefore, since similar triangles, so therefore, I don't need since. Therefore, similar triangles will have the same reduced value of each ratio. Okay? What is the only thing that the sine, cosine, and tangent of an angle depend on? So the actual value of the sine, cosine, and tangent depend on the angle that's used. That's what changes the value of it. Okay, so they depend on the angle measurement. Right, so the sine of 30 degrees will be different from the sine of 40 degrees. because the angle determines that shape of the triangle. Okay. State the three primary trig ratios for the indicated angles as a fraction and a decimal rounded to the nearest hundredth. Okay, so indicated angle here is S. So three primary: sine, cos, and tan. So we'll do sine of S equals opposite over hypotenuse, and then reduce that. I'm going to just reduce it on the same line, and that's equal to, actually, I'm not. Try to use proper form here. So on the separate line, and then here I'm going to say, therefore, sine of S equals 0.8. Okay. Next one is cosine of S. That's adjacent over hypotenuse. That reduces to 3/5. So therefore, cos of S is 0.6. And then tan of S is opposite over adjacent, is 4/3, which is nearest hundredth would be 1.33. Okay. Next one, G. Now, what you might want to do, I didn't do that on the last, I'll go back though. Take a look at the hypotenuse and label it. Then compare it to S, 6 is adjacent, and 8 is opposite. So if you need to do that to start, to help you out, go for it. So here, G, the hypotenuse is 17, the opposite is 8, right, because that does not touch it. This is the adjacent side, but we don't know what it is. Okay, so this is adjacent, so we need to figure that out. Let's call it X, and it's a leg, so X squared is the hypotenuse squared minus the other leg squared. Okay, so calculator, 17 squared minus 8 squared is 225. Turns out to be nice that X is 15. Okay, so now sine of G, so this equals 15. Sine of G is opposite over hypotenuse. Can't be reduced. Let's show it as a decimal. 8 divided by 17, nearest hundredth, if we have to, 0.47. Cos of G is adjacent over hypotenuse. So 15 divided by 17, 0.88. Tan of G is opposite over adjacent. 8 divided by 15 is 0.53, repeating, so it rounds to 0.53. Okay. Then the next column, there's our angle. So this side, 12.3, is touching it. That's adjacent. This side here is touching it, but it's the hypotenuse, right? So this is hypotenuse, and then this would be opposite. So we need to know what the hypotenuse is. So again, we'll call it X. So X squared equals 19.2 squared plus 12.3 squared. Oops, sorry, calculator. So 19.2 squared plus 12.3 squared. And then square root it. And round, so in this case, it's 22.80197336. I'm going to show all my answers because I'm actually not asking you, we are not asking you for the length of that side. So if you round it too early and use a rounded value, then you'll get more error in your final answer. I'm not asking you what the hypotenuse is. I want to know what the sine of D is. So that's opposite over hypotenuse. So that's where I'm going to 7, 3, 6. Okay. And what's nice in this case is, we have it in our calculator already. So I can go 19.2, and then you can either go second negative for dividing. Oh, sorry, I forgot to divide that. 19.2 divide second negative, okay? Or you can go 19.2 divide, cursor up to your answer. Depends on the version of your calculator. Now I'm going to round that to 2 decimal places. Okay, let's see what would happen if I rounded, so if I rounded the hypotenuse to 22.8, turns out I'd still get the right answer in this case. Okay, cos of D, I'd still get the same answer rounded to the nearest, actually almost the nearest hundredth there. D is adjacent over hypotenuse. Okay, so 12.3 divided by, again, I'm going to go up. If you can't go up, then copy out whatever decimal places are on there. And that's 0.54. And then tan of D is 19.2 over 12.3. And 1.56. Okay, notice the values of these, all of the sine and cos values are all less than 1. Tan could be greater than 1 or less than 1. And they're also positives because you're dealing with the lengths of the sides. Okay, so we've already started to use our calculator, but now with the angles. So primary trig ratios exist for almost all angles, and lucky for you, these values are stored in your calculator. Use your calculator to state the value of each of the following trig ratios rounded to 4 decimal places. Okay, in the old days, we had a table. We'd have to look up the angle and then look across the table to find the sine or the cos or the tan. So, So here, want you to check. We are measuring angles in degrees, but your calculator defaults to what's called radians, and you'll learn about those in Math 30. But for now, we're measuring angles in degrees, so you have to go to Mode, Key, and then cursor down. Mine is already on degrees, it's selected, but if you have a cleared calculator at some point, then it's going to be in radians. So go to degree and just press enter on it so that it's selected, it's darker. Okay, so now you can quit out of that second mode, and then let's enter. Tan, there's a button for it. Tan of 32, close the bracket, enter. And it says 4 decimal places, so 0.6249. Then tan of 84. If you don't close the bracket, and that's all that you're doing, doesn't matter. Okay, but if you're doing a multiplication or something like that, then you need to close the bracket. So 9.5144, and sine of 58.9 is 0.8563. And then cos of 18.6 is 0.9478. Okay? Notice how all these values are less than, all of the values for sine and cos are less than 1. For tan, it could be greater than 1, as I mentioned before. Okay? The trig ratio of an acute angle is given. Use your calculator to state the value of the angle rounded to the nearest degree. So for these, we have to work backwards. So we have to do the inverse of sine. So here, to get angle A, the inverse symbol is -1, as looks like an exponent. It really isn't. It means sine inverse of 0.5. How do you get that on your calculator? You go second key, sine key. You'll see it's blue on the actual calculator, which means you have to press the second key, and then 0.5. Okay, so that's 30, and our calculator is in degree mode, so that's 30 degrees. It doesn't show the degree symbol there, but that's what it is, so you need to enter that. Okay, so it's called inverse sine, basically. Inverse tan here, we have to go tan inverse of 2.6341. So second tan, 2.6341 is 69.2. What are we doing? It's the nearest tenth of a degree, so very necessary. Then next one is tan inverse 0.2480. Okay, so second key, tan key, 0.248. You can put the 0 in, but you don't need to. And that's going to be 13.9 degrees. And last one will be cos inverse of 0.8825. So second cos, 0.8825. Oops. 8825, close the brackets, and that's 28.1 degree. Okay, so that's how you use your calculator. If you're given the angle, you just punch it in after entering in the trig ratio. So tan and then 32. In 5a, in 6a, you have to go second sine 0.5. Okay, so the following provides the trig ratios of several angles. So we've done these for you. So basically angles from 0 through 90 every 10. What happens to the sine of the angle? So as we are increasing from 0 to 90, what's happening here? Well, you'll notice the angles are increasing. No, sorry, the ratios are increasing. Here, for cosine, notice it's starting at 1 and then getting smaller. So these are decreasing. For tan, starting at 0 and increasing, it goes actually to infinity for that. Okay, so the sine of the angle increases from 0 to 1. Cosine decreases from 1 to 0. And tangent increases from 0 to infinity. That's the infinity symbol, kind of a sideways. Okay, for what angle is the tangent ratio equal to 1? So if we take a look back, that's for angle 0. Okay, sorry, tangent ratio, I looked in the wrong place. Equal to 1, it's not in the chart. Okay. Okay, so for what angle is the tangent ratio equal to 1? You take a look in the chart, there isn't a 1 in there. It's somewhere in here, between 40 and 50. Let's think about if a tangent ratio, so tan of an angle, let's call it x, is, remember, opposite over adjacent. So how do we get this to be equal to 1? That means the opposite and the adjacent, opposite has to equal the adjacent, right? So what does that look like? If we have a right triangle, here's your x, so our opposite and adjacent have to be equal. Well, if we have two sides equal like that, then that, and it's a 90-degree triangle, then it's isosceles. Isosceles triangle. Okay. Next one, so the next page. Explain why sine 30 equals cos 60. So if we look back in our chart here, sine of 30, cos of 60. Okay, same value. Well, let's think about the triangle. So if we have this being 30 degrees, okay, and this would be, let's call this A, B, and C, then sine of 30 would be A opposite over hypotenuse. Okay, now what's this other angle in here? This is 30, 90-degree triangle. This is going to be 60 degrees here. Okay, well then cos of 60 degrees is adjacent, which is A, over hypotenuse, which is C. And these are the same. Okay, so, and that's because it's a 90-degree triangle, and angles in a triangle add up to 180. So basically, the two angles, these two angles here, have to add to 90. If they do, they will be equal ratios. So here is the sine and cos, so the two angles have to add up to 90. So that would be 15 degrees. Here, cos and sine, these have to add up to 90, so that would be 60 degrees. Here, cos and sine, so these have to add up to 90, so that would be 9 degrees. Okay. For what angle is the sine ratio and cos ratio equal to each other? Explain why. Okay, well, if we look back at this, so our sine, or actually, we'll draw a new triangle here. We talked a little bit about this in the question above. Okay, so sine ratio and cos ratio equal to each other. That means that opposite, remember this is opposite over a hypotenuse and this is adjacent over a hypotenuse. In order for these to be equal, if the hypotenuse has to be the same, so therefore the opposite has to equal the adjacent. Okay? So, think about that. That's got to be an isosceles triangle. We're not quite done because it actually asks us for the value, what angle. So this is 90. If these are equal, these two angles have to be equal, and they have to add up to 90. So basically, each acute angle will be 90 divided by 2, which is 45 degrees. Okay. Then in 12, is there an angle A such that sine of A equals 2.6341? So remember, sine of A is opposite over hypotenuse. Okay, so is that possible? So this says that the ratio has to be greater than 2 when it's simplified. So that would mean that opposite would have to be bigger. So is this bigger, give me a sec, bigger than hypotenuse? No, right? The opposite is a leg of the triangle. The opposite side. So no, the opposite side can never be longer than the hypotenuse. Okay. Angles of inclination, elevation, and depression. So those are some words that you have to know. Angle of elevation or inclination, that's the acute angle between the horizontal and the line of sight to an object above eye level. Okay, so you're going, here's your person, your eye, you're going from basically, if you put your hand out horizontally and you're raising it up. Okay, so that's the angle of elevation or inclination. And then angle of depression is from the horizontal down. So here down. Okay. So you do need to know those words for questions that we may end up doing, the application questions. Okay. Next part here. Sheet. Use trig ratios to determine angle measure. So given the following triangle, determine each of the following as a ratio and as a decimal rounded to the nearest hundredth. So again, we've done some like this before, but we will go through. So remember, in this diagram, if we're doing all trig ratios, we need all of the sides. So I'm going to label opposite the 90 degree as the hypotenuse, okay, and I need to figure out what this side is. So that's a leg. So x squared equals the hypotenuse squared minus the other leg squared. So 144 minus 25, okay, is, so let's do this. 144 minus 25. Oh, sorry. 144 minus 25, 119, and then we have to square root that. Okay, so 119, so x equals the root of 119. Now, we can show the decimal form here, but what I want you to get used to doing is using the radical form. Right? We've already done roots and powers, and so leave it in radical form, and then that keeps it, we can round at the end, but at least it keeps it exact. So sine of A, so I'm going to look at A, opposite is 5, and hypotenuse is 12. Okay, so then 5 divided by 12, the nearest hundredth is 0.42. Cos is adjacent to A, which we just did was root of 119 over 12. So square root of 119. Cursor out of the square root divided by 12 equals 0.91. Tan of A is opposite over adjacent, so that's 5 over root of 119. 5 divided by root of 119. Oh, here again. Oops. Okay, 5 divided by root of 119. And 0.46, nearest hundredth. Okay, if it's got a radical in the denominator, like in tan of A, we will end up rationalizing it. For right now, we're going to leave it like that. Then for B, so now we're at B doing sine, which is opposite, root 119 over hypotenuse. Notice how it's the same as cosine of A. So this is going to be 0.91. You don't even have to use your calculator. Cosine of B is adjacent over hypotenuse. Again, it's the same as sine of A. So that's going to be 0.42. And then tan of B is opposite, which is root 119 over adjacent. And so that's really the reciprocal. So you could go 1 divided by that answer. And with that, I could go, excuse me a sec, clear. 1 divided by, sometimes it doesn't register what I've clicked when I'm on the smartboard here. So 2.18, or do it right like it says, 119, cursor out, divide by 5, gives you the same. Okay. Use any of the ratios above to determine the measures of angles A and B. So now, it doesn't matter which one you do. So I'm just going to use sine of A equals 5 over 12. I'm not going to use the decimal form because it's rounded. So now A, remember, is inverse sine of 5 over 12. So on my calculator, now I go second sine 5 divided by 12. Register it again. 5 divided by 12. Okay, so that doesn't say what to round to. We'll go to 1 decimal place usually for angles. Okay, Now, if you had used second sign of that decimal form, which was rounded, second sign, second, there we go, sign of, if you've gone 0.42, you would have, it would be a little bit off, 24.8. So you get a half mark taken off, right? Because you rounded too soon. So just be aware of that. Okay. And then we get into some application examples. So to be safe, a ladder should have an angle of inclination of about 75 degrees. 14-foot ladder is placed against a vertical wall such that the foot of the ladder is 3 feet from the wall. Is the ladder in safe position? So basically draw a little diagram. So there's the ground. Here is a wall. Okay, I'm going to try to move that a little bit down. There we go. And then a ladder up. And again, I'm going to try to move this. Okay, so this is the ladder. And so we want to check the angle of inclination is this angle in here. And so is it 75 degrees? Because that's where it's going to be safe. Now remember, it's a 14-foot ladder, so label 14. We're assuming the side of the building is vertical, the wall. And the foot of the ladder is 3 feet from the wall. Okay. So don't bother finding this side that's missing. We just need to find the angle. So we are given here, this is the hypotenuse, and this is adjacent. So A over H is cosine. So cosine, I'll call it X, equals 3 over 14. So X equals inverse cos of 3 over 14. So calculator out. And we are going to go second cos 3 divided by 14, and that is 77.6 degrees. So it's a little bit too steep. Okay, so that's greater than 75 degrees, therefore a little too steep. So not safe. Because if you've ever been on a ladder and you're too close, if it's too steep, it kind of feels like you might end up, if you lean backwards a little bit, you might end up looking backwards. Now it's pretty close, but it's a little bit more. So I think maybe in our notes, we've said it's okay because it's close, but I would say it's a little bit too steep. So we'll probably say, give a little bit more specific if between certain values so that you know that you can answer correctly in your statement answer. Its sides, if the width of the rectangle is 3.4 centimeters, so label 3.4. That's the same as this. Length is 8.1. That's the same as this. And we want the measures of the angles between the diagonal of a rectangle. Well, there's more than one diagonal. You can do it either way. It doesn't really matter. But I want to know what this angle is here and what this angle is here between the sides. Okay? So let's call this one X and this one Y. So notice in X, this is a rectangle, so this will be 90 degrees. So we have the opposite side and the adjacent to X. So that's tan. So tan of X is opposite over adjacent, and that is 3.4 over 8.1. I'm not going to find the decimal form because I really want the angle. So remember that's tan inverse of 3.4 over 8.1. Okay. Okay, and so second tan, 3.4 divided by 8.1. Oh, the second didn't show up there, sorry. Second tan, 3.4 divided by 8.1. Okay, and 22.8 degrees. Now, we don't really have to do another trig to calculate this because if you take a look at this, this has to be 90 degrees in total as well. So therefore, y would be 90 degrees minus 22.8 degrees. Okay, so then 90 minus that answer, and that's going to be 67.2 degrees. Okay. Number 3, on one part of the bicycle pathway along 14th Street in the northwest, a cyclist travels a distance of 1 kilometer along the pathway while gaining 80 meters in elevation. Okay, determine the angle of inclination of the pathway to the nearest. So basically I'll draw here, so there's horizontal, here's the pathway. Okay, I'm going to move that down. Okay, so it touches, and then, so here we have, it can form a 90-degree triangle here, right? The horizontal continues forever. But this is the path that they travel 1 kilometer along the pathway, so it gains 80 meters in vertical height, okay, in elevation. So, determine the angle of inclination, which is this. Sometimes we use variables, sometimes we use theta, Greek symbol that's often used for angles. So we'll start using that as well. Notice how the units are different here, so I want to show this as in meters, okay, so that we get the correct ratio. So we want to know that angle of inclination. We know here, we know the opposite and the hypotenuse. So that's going to be sine. Sine of theta is 80 over 1,000. Again, you don't have to reduce it because we're not asking for the ratio, we're asking for the angle. So that's what it's going to look like on your calculator. So second sine 80 divided by 1,000, and that's going to be 4.59 degrees. Right? It's going to be a small angle, otherwise it's really hard to bite that. Okay. So a new tree is planted in the ground. The tree is to be pegged to the ground with 2 4-meter long ropes that are attached to the tree 2 meters above the ground. Determine the angle of inclination between the ropes and the ground. So again, I'll draw that ground. My nice little tree. And then the ropes. Pegged to the ground with 2 4-meter long ropes. 2 meters above, yeah, so just estimate as best you can, something like that. And then same on the other side, I'm going to need to move this. All right, so these are the same. So this is equal to this, 4 meters, 4 meters, and 2 meters above ground. Okay. So there is, maybe I'll do that vertical line. Okay. So the center there, so that meets at 90 degrees. And so we want to find this angle here. Again, I'll call it theta. So we know here the opposite to theta and the hypotenuse to theta. Okay, so we're going to go sine of theta is 2 over 4. So theta, now that's a half, so I would probably just put this in as 1 divided by 2, or 0.5. So second sine, for some reason it's not liking, there we go, second sine, 1 divided by 2, and that's 30 degrees. And then using trig ratios to determine side length, state the value of each of the following ratios given the right triangle shown. Round answer to 4 decimal places. So here we're just given the angle, 29 degrees. Okay. So if we're looking for opposite to angle A over hypotenuse, so this is opposite and this is hypotenuse. Okay. Well, what's opposite over hypotenuse? That's sine. So this is equal to sine of 29. Okay. And so in our calculator, we can do that. We don't know what those sides are, but we know the ratio of those sides because remember the ratios are stored in our calculator. So now we just go regular sine of 29 degrees, and it's always going to be a decimal, less than 1 for sine or cos, 4 decimal places, 4, 8, 4, 8. Then adjacent to angle A, well, adjacent to angle A would be here. And adjacent over hypotenuse is cosine. Okay, so then second cos is, sorry, not second cos, cos of 29 is 0.8746. And then opposite over adjacent is tan of 29. Okay, so tan of 29 is 0.5543. Okay, and then example 3 says if the length of the hypotenuse shown is of the triangle shown above is 15.7, then use the ratios you found to help determine the lengths of the two sides. Right? So if we look back up here, we now know the length of the hypotenuse. So really here, this is 15.7. This is 15.7. Okay, so we can, we know for the first one, so opposite over 15.7 equals 0.4848, and we can solve for the opposite, right? So 15.7 times 0.4848. Now, saying that, we're not going to use that. Instead of 0.4848, we're going to use sine of 29, okay? Because that is more accurate. All right, so when we do that, we will get the length of the opposite side. So here, we'll go 15.7 times sine of 29, and that is 7 point, I don't know if it says, we'll go to 1 decimal place, so 7.6, right? We don't know the units. And then you could use Pythagorean theorem with the unrounded value, or I would use trig again because it's a little more accurate. So we found the opposite, we are told the hypotenuse, so we need adjacent. So then adjacent over hypotenuse, remember, is cos of 29. Sorry, we know the hypotenuse is 15.7. So that means adjacent equals 15.7 centimeters. So we know adjacent equals 15.7 times cos of 29 degrees. So 15.7 cos of 29 is 13.7. Right? Okay, example 4, given that angle A in the right triangle shown is 58 degrees. So we can label that 58 degrees. And the length of the adjacent side is 5.2. Determine the lengths of the other two sides to the nearest 10. So we want to find the opposite and the hypotenuse. Alright, we know the adjacent. So let's find the opposite. So you have to use adjacent to help you find the other side. So here we'll have cosine of 58 degrees is adjacent over hypotenuse. And we'll have tan of 58 degrees is opposite over adjacent. Okay, that will give us the two other sides. Let's do the tan one first because our unknown is in the numerator here. So that means opposite is 5.2 tan of 58. Okay, so 5.2 tan of 58 is 8.3. Okay, so it's just an equation that you're solving. The opposite of dividing is multiplying. So really what we're doing here is multiplying both sides by 5.2. Okay, here are unknowns in the denominator. So we need to multiply through by the hypotenuse. So if you can see this, so hypotenuse there, hypotenuse here, those divide out. So then to get the hypotenuse by itself, you have to take 5.2 and divide by cos of 58. So all you need to remember is if you're looking for the opposite side using tan or sine, then you're multiplying. So if your unknown is in the numerator of your ratio, you're multiplying. If your unknown is in the denominator of the ratio, you're dividing. You're always multiplying by the trig ratio or dividing by the trig ratio. So now 5.2 divided by cos of 58 is 9.8. Okay, and what is this? What kind of units? Inches. So inches. Right. And next one. So Angelina in the hot air balloon spots a bag of money on the ground below. She radios to Brad, who is standing directly below the balloon. To run to the money bag. If the angle of depression from our line of sight to the money bag is 38 degrees, we can label that for you. So that's 38 degrees. It's not in the triangle. So if we draw the triangle, the 38 is not in it. But what you should remember is your parallel lines theorem from junior high. These are parallel, horizontal and horizontal. Those are arrows. Okay, so this 38 will be 38 down here. So now we do have an angle within that triangle. Her height above the ground is 215. How far does Brad have to run? So what is this? Okay, so given 38 degrees here, this is the adjacent side, and this is opposite. So use tan. So tan of 38 degrees is 215 over the adjacent. I'll call it x. So remember, your unknown is in the denominator, so that means you divide by the trig ratio. Okay, and then do that. We have 215 divided by tan of 38. Okay, and that's 275.2. Okay, and then let's go to the next question. Example 6. Sarathana is flying a kite in Glenmore Park. At one point, she has let out the entire 156 feet of string that is attached to the kite. So that's 156. The angle of elevation for a line of sight to the kite is 54 degrees, and the string is taut, which means it's tight. Okay, so line of sight then, this, oh, that's not a good horizontal. Sorry, oops, just a sec. Let's fix that. So let me draw in, so basically here. Okay, so line of sight. Okay. Okay, so this is 58 degrees. 54 degrees. Okay, determine the horizontal distance to the kite. Okay, horizontal. So basically from here, we're going to draw a horizontal. Or we draw the horizontal, we're going to draw a vertical, and we want to know what this distance is here. Okay, so that is the adjacent, and we know the hypotenuse. So here, this is adjacent, and this is hypotenuse. So that would be cosine. So cos of 54 degrees is x over 156. So we're going to multiply those together. And then 156 times cos of 54. Okay. And so x equals 91.7, and that's feet. Then determine the height of the kite above the ground, and there's 10. If Sarathana is holding the kite at eye level and her eyes are 5 feet above the ground. So basically, here's the ground, right? Here's her eye level, so this is 5 feet. So we need to know what this part is, and we'll add 5 to it. So within the triangle, that's opposite, and we know the hypotenuse. So sine of 54 degrees is y over 156. Now you could use, now that you know x, you could use tan, but then you would want to go back and use the unrounded value for 91.7, not the rounded. In any case, we solve for y here. So y is going to be 156 sine of 54, and that's 126.2. And then, so the height above ground, we have to add the 5 to it. So plus 5. 131 to okay. And then solving right triangles. Solving right triangles means you're finding all the angles and all the sides. So that's what's in the box there. To solve a right triangle, find the lengths of all the sides and the measures of all the angles. You need to be given at least 2 sides, or 1 side and 1 acute angle, along with the 90 degrees. So solve triangle ABC, round values to the nearest 10. So here we're given 2 sides. So to find this side here, you could use Pythagorean theorem. You don't even need to use trig, right? You can't use trig at this moment because you don't have an angle, but you could later. And I'm going to find that right now. So x squared equals hypotenuse squared minus the other leg squared. So 19 squared minus 14 squared, 165. So x equals the root of 165. It does say to round. So we'll do that. And it's 12.8 centimeters. And angles. So let's find angle A. Okay. This is adjacent. And this is hypotenuse. Don't use x because it's rounded. If you do use x, you can, but use the root of 165. So I'm going to use the ones that are given. So that's adjacent over hypotenuse, which is cosine. So cosine of A is 14 over 19. So A is inverse cos, 14 over 19. So second cos, again, second cos, 14 over 19, over 19, and that's 42.5. And we don't need to use any trig for the other angle because we know that the two angles have to add to 90, or all three have to add to 180. So therefore, B is 90 minus 42.5. $47.5. Okay. So we've got all the values and all the sides. All right. Okay, and then example 2, PQR, if P is 35, Q is 90, and R is 85 inches. So we want to draw a triangle as best you can. So here we know Q is 90 and P is 35. So I'm going to go like this. Okay, so this would be Q, that's 90. This is P, that's 35. And R, so when you label a triangle, this is triangle PQR, so PQR, the sides are the lowercase letter of the capital letter of the angle across from it. So this would be little p, this would be little r, and this would be little q. So that means little r is 85, and we don't know what these are. Okay. Now, saying that, we can find angle R, because it's a 90 degree, and we know P is 35, so that'll be 90 minus 35. So that's going to be 55 degrees. So we've got that. And then let's find the sides. So compared to 35, this is adjacent, this is opposite, and this is hypotenuse. Okay. So let's do opposite first. So try to use adjacent in your ratio. So opposite over adjacent is tan. So tan of 35 is, I'll call it lowercase p, the opposite over 85. So p equals 85 tan 35 degrees. So 85 tan of 35 degrees. That's 59.5. What are we measuring this in? Inches. Okay. And then for the hypotenuse, that I want to try to use adjacent. I don't really want to use a rounded value and go back and use the exact. Takes more time. So that adjacent and hypotenuse is cosine. So cosine of 35 is adjacent over hypotenuse, which is Q here.
So now my unknown's in the denominator, which means I need to divide. So 85 divided by cos of 35 degrees. So 85 divided by cos of 35 degrees equals 103.8. Again, that is inches. So make sure that that Q value is bigger than P and R. Okay, and it is. So that makes sense. Okay, and we're finally done.